Hello again, it's Dr. Kofelt. We're going to talk a little bit now about empirical formula and percent composition. And we introduced empirical formula a little bit earlier, but now we're going to show you actually how that is calculated and where it comes from. And we had to understand about molar masses before we could do this. So if you recall, empirical formula is the simplest whole number ratio that the formula can have. And so we're going to show you how we can experimentally determine percent composition, which then will allow us to calculate the molar mass. Get my pen right now. There we go. All right. So these are the steps for taking percentages to grams and using the percent composition to do empirical formula. So a lot of times you get it in percent composition, as I said, and so those percentages we're going to convert to grams. So since it's a percent, that means it's how many out of 100. So you can assume, instead of calling it a percent, just say it's 100 grams. Okay, and so if you've got 24.5% carbon, that would mean you had 24.5 grams of carbon. And when you do that, then you can use those grams, use the molar mass, and figure out how many moles of each thing you have. Now, once you've done that, you're going to get some odd numbers that have decimals. So what you're going to do is then you're going to divide each one of those numbers by the smallest number of moles, and then you will obtain a ratio of one of them being 1, okay? And so it'll be a 1 to something ratio. And then you figure out what you have to multiply it by to get all of those numbers to be reasonably close to whole numbers. And that is how you will know the empirical formula of your material. So determine the empirical formula of a compound that is 30.45% nitrogen and 69.55% oxygen by mass, and notice those equal 100%. So remember I said if I've got 30.45% nitrogen, I'm going to say in a 100 gram sample, that's the same as saying 30.45 grams of nitrogen. And in the same way, 69.55% oxygen is 69.55 grams of oxygen. And I know that in a formula, they're not in grams, they're not in mass percentages, they're in molar percentages. So what I've got to do is I've got to convert each one of these to moles. So I can look up on my periodic table for nitrogen. I know nitrogen is approximately 14 grams in 1 mole. So that's going to give me moles of nitrogen, and that comes out to be 2.175 moles of nitrogen. And then oxygen is 16 grams. Okay. And then 69.55 divided by 16 is going to give me 4.347 moles. Now, I can't have a formula of N 2.175O 4.347. So what I do is I'm going to divide by that lowest number, which is 2.175. I got to do it to both of them. So that makes one of them 1. And the other one is going to be really close to 2. So that tells me that I have 1 nitrogen and 2 oxygens. So my empirical formula is going to be NO2. Work? Okay, not hard so far, right? Okay, so here's your for practice in doing this as well. So this one down here, you've got 3 things, okay? So convert those to grams in a 100 gram sample, find the moles, divide by the lowest one, and then get that ratio. And if it's still not to an even number, then you may have to multiply it by something else to get whole numbers. So like if you have 0.25, you might have to multiply it by 4 to get that one as a whole number, and hopefully if you multiply everything by 4, you'll get whole number ratios. All right, so this is all part of part 5. So we're going to talk about how we get this empirical formula, and then how we can actually use the actual molecular weight we find to calculate the molecular formula. All right, so knowing the mass of each element in a sample enables us to determine its empirical formula. One way we can do this is through combustion analysis, and we know combustion is burning, okay, and so we're going to burn this stuff, and then we're going to capture the gases that are produced in these absorbers, or some instruments call them scrubbers, and we are going to then trap those. So we've got a sample of material in here. We have to have oxygen in order to combust something. We've got a furnace where we're going to heat it up really high, and so we're going to burn this thing, and we're going to convert it to water and carbon dioxide. And then we might have a few other things, but if it's a hydrocarbon, then that's all we're going to get out of it. So if we have something like glucose, for example, glucose is C6H12O6. Okay, so it's only got carbons and hydrogens and oxygens in it. And when we combust that, we're going to get CO2 and water. And since the only oxygen, we're only adding oxygen, I should say, to the reaction, carbon and hydrogen can only come from the glucose. Now the oxygen could come from the glucose, but it could have also come from what we added. So we're going to actually calculate the CO2 and the water, the H2O that we produce, and then we will use those masses to figure out what the empirical and then finally the molecular formula is. So these masses were determined experimentally from the combustion of glucose. All right, and remember, we have C6H12O6, but we may not know that. It may be unknown. We may not know if it's glucose. All right, so when we do that, we get, and this time we're already have it in grams. Okay, so we had 7.53 grams of carbon, 1.26 grams that we absorbed of hydrogen, and 10 grams of oxygen. And so when I convert to moles of carbon, I get 0.627. When I convert to hydrogen, I get 1.25. And then when I convert by dividing by 16 grams, I get 0.626 moles of oxygen. So if I was just going to use those numbers, my formula would look like that. C 0.627, H 1.25, O 0.626. But now I know I can't do that. So remember, I got to divide by the lowest one, so at least one of them will be a 1. So I divide this one by 0.626, this one by 626, and then this one by 626. Now that gives me, this one is really close to 1. And I mean, they're not going to be exact because it's experimental, right? So we have some things that may not be perfect, but we get 1. And then when I divide this one, I get really close to 2. And then this one, I get close to 1. So that tells me I have 1 carbon, 1 hydrogen, 2 hydrogens, and 1 oxygen. And so my empirical formula is going to be CH2O. And remember, glucose is C6H12O6, which the molecular formula would, if I divided by 6, would give me that as the empirical formula. So that makes sense. So I do know that the molar mass of glucose is 180 grams. The empirical formula of glucose, which is CH2O, is about 30 grams, okay? So I've added those together, 16 plus 2 plus 12. That gives me 30 grams. So if I want to know what the molecular formula is, like the actual formula, not the empirical, then I divide the molecular mass by the empirical mass, and that gives me a factor of 6. And so then all I have to do is multiply my CH2O by 6, and that's going to give me C6H12O6. So that's how I am going to go from empirical formula to molecular formula. So combustion of a 5.50 gram sample of benzene, you don't have to know what that is, okay, produces 5.073 grams of carbon, 0.426 grams of hydrogen. So that's all it's got in it, is carbon and hydrogen. Determine the empirical formula and the molecular formula of benzene if the molar mass of benzene is 78 grams per mole. So I'm not going to use that molar mass until the end, because I've got to find the empirical formula first, and then I use the molar mass to figure out what the molecular formula is. All right, so what I'm going to do is first I'm going to see what the percentage is, okay? So for carbon, I have 5.073 divided by 5.50 grams. So that's grams of carbon divided by total grams, and then times 100, right? Because I'm going to do a percent. And that's going to give me 92.236%. Now hydrogen is 0.426 grams of hydrogen from my original sample, which was 5.50 grams of sample, times 100, and that's going to give me 7.745%. And yeah, you could just subtract it from 100, but it's a good idea because sometimes it's off just a little bit, like on that second or third decimal place. So I usually just go ahead and do it, and it comes out a little bit closer to what you're looking for. All right, so I'm going to translate that to grams. So 92.236 grams of carbon times 1 mole of carbon is 12.01 grams of carbon, which gets rid of grams because I got to have that molar ratio, and then 7.745 grams times 1 mole over 1.008, right, grams of hydrogen, okay, and then that's going to give me 7.6799 moles, and this one's going to give me 7.745 moles of hydrogen. So remember what I've got to do. You can kind of tell it's a 1-to-1 already, but technically we're supposed to divide that by the smallest one, which is the 7.6799. 7.6799. So those are both going to be approximately equal to 1. And so that tells me that the empirical formula is going to be CH. That's pretty simple, 1-to-1. All right. In order for me to find out what the actual molecular formula of benzene is, I need to first see what the empirical formula weight is, and that's pretty easy. That's 12 plus 1 equals 13 grams per mole. It told me that the molecular is 78 grams per mole. So remember what I do? I divide the big one by the little one, so 78 divided by 13 is 6. And so my molecular formula, I have to multiply my empirical formula by 6. So that's going to be C6H6. Because remember, if I don't have a number down there, we understand that it's a 1. Because chemists are lazy and we don't like to write anything we don't have to. Okay? All right, so C6H6. And so you have a practice one to practice this, and I encourage you to go ahead and do that now so that it'll be fresh on your mind, and so you'll be ready to do homework or whatever other studying you're going to do. All right, and I'll see you back for part 6.